Okay, so I've often been interested in how number systems come about. I'm looking for geometric explanations for why number theory has the structure it does. So I was thinking a while ago about circles and how we could represent multiplication by circles. So if we use circles which are twice as big like that, these can represent our multiples of 2. So to cross this line at point 0, 2, 4, 6 and so on. And then we could have circles which have size 3. And we can keep drawing those, etc. So this was one idea, but today I want to talk about something a bit closer to the core of connections between geometry and rational numbers in particular. So let's have a look see at that. And the key idea comes from projective geometry, and it's the idea of a harmonic conjugate. So suppose we have a line, we'll call the line L, and we have 3 points on it. Okay, and I'm going to tell you how to construct a point. It's the harmonic conjugate of A with respect to points B and C, and it's going to be a point on this line. So how do we construct it? Well, we pick either of these two, so it doesn't matter which order we do this. So this is the same thing as this. So anyway, we pick either of these points. Let's pick C, and we draw any two distinct lines through C. I'm just going to mark these lines with a little squiggle, and we draw any line we want through A. I'm going to mark that with a squiggle. Now you see these new lines we've drawn, they make two new points up here. And we have a sort of, so basically we draw a kind of structure where we have sort of V shapes, as two lines coming out of C and coming out of B. So we draw a sort of V shape with these two new points, like so. And you see that we make two new points like so. And now if we consider these 4 points that are not on the line, 1, 2, 3, 4, those are what you call a quadrangle. And you see that if you think about the different lines that you can draw between pairs of these 4 points, most of those lines have been drawn in. In fact, there's just one line missing. And that line there meets this line at a point D, and that's actually this value that we want. So the remarkable thing about this construction is that it doesn't actually matter how you choose these initial lines through C and through A. So there's a lot here. I know I'm not proving this, that this is well defined in the sense that you always get the same answer no matter how you choose those lines. But there's a lot to go through, so I'm going to move on, and if you're interested in this you may want to re-watch the video, and I'll put a link to some further resources where you can see more background about this harmonic conjugate operation. So just to summarize, this thing here is the harmonic conjugate of A. With respect to B and C. Okay, so now let's get to the remarkable claim. So the remarkable idea here is called a net of rationality. So we have a line, which we shall call L again, and we're going to have 3 points on this line. Now, there's nothing really special about these 3 points, but I'm going to give them rather loaded names, which I ask you not to think too much about yet. So these 3 points, we're going to call them 0, 1, and infinity. Okay. And now what we're going to do is we're going to start taking the harmonic conjugates using 3 points. Okay, so let's begin. Let's find the point which is the harmonic conjugate of 0 with respect to 1 and infinity. Okay, so how do we do that? Well, we pick one of these points, let's say infinity, we draw a couple of lines through it, and then we draw a line through our object that we're operating on, 0. We get these 2 new points. We construct the V through 1. And you see we get a new point here. And in fact, we're going to call that number 2. So imagine we had a set. And this set here, it contains the points 0, 1 and infinity. So they're going to be in our set. So this is going to be a set of points on this line. And it holds 0, 1 and infinity. And also it has the property that if x, y and z are distinct members of S, then so is the harmonic conjugate of X with respect to Y and Z. Okay, so this is, let me hold this up. This is our critical definition because this defines, so when I say so is this, I mean this is also in S. Okay. So what this basically does is it defines this set S of points on the line, and that's called a harmonic net or a net of rationality, and that structure is basically equivalent to the structure of rational numbers on our number line. So if you think about all the rational numbers, or as many as you can, there's 3 over 2, 5 over 1 and all that kind of stuff. Those are a load of points on the line, and this basically gives you an equivalent way to construct that set, but purely using projective geometry. So we're just using straight line constructions here. Now, there's something about this point at infinity. In the constructions, you basically can treat it like any other point, and in fact you have a whole line of points at infinity on your projective plane, and you just carry on. But then there's also a sort of affine view of these constructions, which is how I first learnt about them from Norman Wildberger's videos. And in those affine constructions, you sort of use this special nature of points at infinity by thinking about things in terms of parallel lines, and those give a much more sort of intuitive description. But basically, I've already shown you how we can use the these harmonic conjugates to find point number 2, and hopefully you can see that we could repeat this again. So the harmonic conjugate of 1 with respect to 2 and infinity is going to be a point 3, and all of this sort of thing makes sense with respect to the sort of labels I'm giving them. So this thing acts like 3 as long as these really are points at infinity. So let me see if I can explain. So basically, if we're going to construct point 3 now, Okay, and so how do we do this construction again then to find this point number 3? Well, basically a good way to think of this whole construction, we'll label this line here. I'm going to give it a rather loaded name, which we'll discuss later, called L infinity. And it has a couple of important points here. It has this point here, which we shall call up, and this point here, which we shall call down. Now, to get point 1, we take point 0 on the bottom line here, and we draw a line through this up, and we project it up onto this line here. And then we shine a light through this down point, and where that hits this bottom line, that gives us our point 1. Then to get point 2, we shine it up here, and we shine it down here using the down point. And then here we project it up using the up point onto this line, and we project it down using this down point onto here. So to find point number 4, we just continue the same pattern, up like so, down like so. That would be 4, and 5, and so on. So what does this have to do with real number systems? Well, these sort of sure look like the integers in the sense that there's a sequence of them, but they don't look like the integers in the sense that they're not all equally spaced. In fact, you'll see they get more and more crowded together as we go towards infinity here. But what about if this really was a point at infinity? If we get moving this to the right, well then these really would be equally spaced points. So I've shown you how you can use repeated harmonic conjugate operations to generate your integers. Well, you probably don't believe me yet, but I shall try and explain a bit more carefully. So anyway, I also want to show you that you can get your fractions, your numbers in between these points, from repeatedly doing harmonic conjugates. So remember the claim. The claim was that if we start with 0, 1 and infinity, and we just keep taking triples of points and finding the harmonic conjugate with respect to using such a triple, and adding that to our sets, so then we get a new point, and we could use that to construct more and more. We carry on. We get this sort of infinite set, and I'm claiming it's basically the same thing as the rational numbers. So far I've shown you how we can use repeated harmonic conjugation to get the integers, although you probably don't believe this because it's not really set in familiar contexts perhaps. So now let's talk a bit about meaning. So this line that I called L infinity, imagine we have a projective plane here. So the projective plane is a model of geometry where we include the idea of points at infinity, and we actually sort of suppose that if you go off in any direction, the projective plane, you hit this sort of line at infinity. So there's a sort of line that's almost like a giant circle of points at infinity. And when you're actually doing projective geometry, you basically say, well, there's nothing special about the line at infinity. I want to treat all points and lines on an equal basis. And so then basically when you're drawing things, you can just pick any line you want and say, that represents the line at infinity. And here's what I represented as L infinity here. Now, another thing I want to label on this diagram is this line here, which I shall call K. And this up point here, I can keep calling it up, maybe I'll call it a U. And this down point here, I'll call it D. And this point here I shall call 0 dash, and this will be 1 dash, and so on. So let's now remember this picture. Now I'm going to draw an analogous version. Maybe I can just take this off actually. Right, so let's draw an analogue of this in the affine plane. So in the affine plane, it's just like the projective plane, where we can only draw straight lines and stuff, except that we really do treat these elements at infinity differently, and we don't ever draw them, but we represent lines that meet at points at infinity as parallel lines that have the same direction. Okay, so let's do the same construction. So we start with our line L, and we have our points 0 and 1. And we're not drawing the point at infinity because it's really off to infinity now. So that's our line L. Now let's draw our line K. So L and K meet at a point at infinity. So the way that we picture this in our affine plane is with a line K, which is parallel to L. Now what we do, well, what we did here was we projected this point 1 up onto K via a particular point on this line at infinity. So basically just draw a line, any line we want, from 0, projecting it up onto a point 0 dash over here. And then this, we projected with this point here. This U point here is really at infinity. Okay, so U is somewhere way over there, and it's so far away. Lines to U are basically just parallel lines, so U is basically specifying a direction. And then we have another point D, and we use that, so we just draw another line like so. And we have this point D, which again is way over at infinity and defining a direction. So now we take 1 and we project it up to U again. So that would be another line parallel to this one because U's so far away. And then project it back down with a line from D, which is just going to be parallel to that other line we drew. And so that will be point number 2. And you can see how intuitive this is, and hopefully you believe that this is going to give you your equally spaced integers. So we go this far, but I want to go further and get fractions. So let's continue this construction. Let's just extend out some of these lines a bit further. Okay, so I want to give these some names. I've already given that the name 0 dash, but I want to give it another name as well. Let's call it A, and we'll call this point B, and we'll call this point C. So now what we're going to do is we're going to imagine we have another point at infinity. Again, we could represent this in terms of that diagram, but we won't for now. We'll do it in the affine plane. So, and we're just going to draw a line connecting this point C here with point number 1. So let's do that. And now let's imagine that there's some other point Z at infinity that defines that direction. So we draw another line through Z, another parallel line in other words, and that should meet this line at the point 2/3. And if we draw another line parallel through A, we get the point 1/3. So let me just zoom in. I'm sorry if this is a bit unclear. What I'm basically saying is if we get this point up here, and we connect that with a line to point 1, and then we draw a parallel line through point, so this is C. If we draw a parallel line through B, that'll meet our line at point 2/3, and if we draw another parallel line through A, which is the same as point O dash, that'll meet our line at 1/3. So this is showing how we're getting fractions, and you could extend this picture, and basically you can get your fractional points on here. So you can always use this kind of method to find the point 1 over k for any integer k. And once you've found that, then you can use this kind of technique to fill out the rest of the lines. Now, I claim that this construction here is essentially what I saw on Norman Wildberger's video. I can't remember if it was the deep structure of rational numbers or the most important unsolved problem of mathematics, the continuum. But in one of those videos, it gives a lovely explanation of how one can do arithmetic in terms of these affine constructions. But I wanted to emphasize that essentially the structure of irrational numbers can be understood from a sort of projective viewpoint, as sort of Coexeter, Lawrence Edwards and various other projective geometers know, in terms of such a sort of net of rationality. We basically start with 3 points on a line, and by doing harmonic conjugates, using any triples, any ways round, and extending this set of points on a line, and picking 3 of them, getting a new one, picking 3 of them, getting a new one, in all the different ways you can, you basically get the structure of irrational numbers. And I think this is very interesting because the rational numbers are obviously extremely important in maths and science, and why is it that they emerge so naturally out of geometry like this? And what does that mean about the irrational numbers? Where's their nice sort of geometric backstory?